Hello all. Today, let we learn about logical gates in Boolean algebra and logical gates. So, as we learned in last session, the Boolean algebra postulates. Now, we are going to design the digital circuits using your logical gates, where logical gates are the fundamental basic building blocks of your digital system. So, a collection of individual logical gates which are connected together, which can form a logical design, or we can call that as a logical circuit. A logical gate is the one which is having two or more number of binary inputs with single output. So here I've mentioned the block diagram of your logical gate, where it can accept n number of inputs with single output. Both input and output are in the nature of binary. So only a gate which is having minimum number of inputs are one is your NOT gate, and the remaining all gates are having minimum number of inputs are started with the 2 to maximum number of inputs you can connect it to a single logical gate is n. So it can implement the outputs, so which is based on your inputs binary combination. Now, basically, our logical gates are classified into three categories: basic logical gates, universal gates, and special purpose logical gates. Basic logical gates are of three types: not, and or. So, these three logical gates can perform the different logical functions. We can derive their logical functions by combining all the inputs and by observing for each combination of input what will be their output. So we can design a digital circuit by interconnecting these three basic gates: and, or, and not. A NOT gate is the one which is also called as an inverter, and it is the simplest form of a digital circuit which can always give the output which is complement of its input. So it will always gives the output which is always the complement of your input. Now, for example, if we give your input with a binary value of 0, you can obtain the complement of your input as an output of your inverter, which is logical 1. So if you are applying logical 1, you obtain a logical 0 is the output. Now we are going to define your each logical gate with their logical symbol along with their truth table. A truth table is one which could have your possible input binary values and their corresponding outputs for each combination. So these rows of your truth table depends on your number of inputs that a gate can have. Now, a NOT gate is the one which is only having one input. So hence we replaced that single input binary value with a possible 0 and 1, and your output is always complement of its input. For 0 we are obtaining 1, for 1 we are obtaining your 0. So your output expression of your NOT gate is always it is complement of its input. So we have indicated that with a bar as on your A. So or you can also put that as a dash. So or negation of A. So these are all the representation of your output expression. So which can give you the Boolean expression of your output that can give you the relation between your output and input. So a logical gate or a NOT gate which is having the input A always gives you output of which is a complemented input. Next we will move to your next gate, which is AND gate. AND gate is a logical circuit which can have minimum of 2 inputs to n number of inputs you can connect it with a single output. the operation of your gate is such that output of your AND gate is a binary 1 if and only if all the inputs are binary 1. Similarly, if any one of your input or more than your one input is 0, the output will be binary 0. So if all inputs are 1, then only the AND gate will generate your output which is equal to logic 1. If any input or more than one input is 0, output of your AND gate will give you the 0 output. So we have mentioned the logical symbol with the 2 input and their output expression or Boolean expression y is equal to a dot b. The logical operator which we are going to use for an AND operation is a dot symbol, or a missing operator between the variables is also the representation of your AND operation between your inputs in order to obtain your output. OR gate is another basic gate like your AND gate. So it also have minimum of 2 inputs too. You can connect it with a n number of inputs and single output. The OR operation will give you the logical 1 output if any one of its input is logic 1. So it's like a mathematical addition, but not exactly the addition. We were not going to have the addition result here. A logical operation of OR we are obtaining by observing its output input combinations with if any input is 1, output logic of your OR gate is 1. If all inputs are 0, then your output of your OR become 0. So now we are going to represent the operator of your symbol of OR gate with a plus symbol, but we will pronounce that symbol with a OR of b, not a plus b. It will be a OR of b. So it can also accept minimum 2 inputs to n number of inputs also. So we can connect it. So with the y is equal to a OR of b, OR of c, OR of d with the n number of input variables. So it will give you the output to 0 if all inputs are 0, and it will give you the logical 1 output if any input is 1. Next, we have basically the second classification under logical gates is universal gates, where NAND and NOR gates are comes under your universal gates, since we can implement any Boolean function which is in the form of sum of product or which is in the form of product of sums using your NAND and NOR gates. So now this NAND gate is defined like complement of your AND is nothing but your AND NAND. So now it outputs a false value if all inputs are 1, and it will output a logical 1 output if any input is 0. So this is the logic behind your NAND gate, and your logical operator we are going to use, which is a AND of b whole bar. So always it will complement the AND. So hence we connected a NOT gate at the output of your AND. So our Boolean expression is y is equal to a AND of b whole bar. Actual logical symbol with the 2 input we mentioned here. Output is a complement of your AND operation. So in order to replace this NOT gate, so we just encircle the output of your AND with a bubble which denotes the logical symbol of NAND, which is a universal gate y is equal to AB whole bar. So it also accepts minimum of 2 inputs to n number of inputs. So we could also have your operation with n number of input variables. A NOR is another example of your universal gate. So which is always, it is inverse of your OR operation. It will give you the output logic 1 if all the inputs are 0. If any input is 1, output logic of your NOR gate is logical 0. The logic expression is y is equal to complement of your OR. So we have indicated that as a OR of b whole bar. Now output of your OR is NOTed or inverted. So hence we have connected a NOT gate at the output of your OR. So which will give you the NOR operation. Instead of that, so actual logical symbol is output of OR is bubbled. So we obtain the logical symbol of your NOR gate. So with this NOT connected at the output of your OR, Y is equal to AR of B whole 1. These XOR and XNOR are the special purpose gates which we are going to use in your digital circuit in order to obtain the outputs of your XOR and XNOR, which is used as a X, we are going to use that as equality detector as well as a inequality detector. So always, so these two are complement, these two outputs are complemented to each other. XNOR gate returns the output which is exactly the complement of your XOR. Same manner, XOR is complement of your XOR. So we also denote exclusive NOR or exclusive NOR in the short form with XOR and XNOR respectively. So XOR gate logical symbol we mentioned here, and the logical operator is used a plus symbol which is uncircled. So and the Boolean expression is represented as A bar B or of A B bar. So the logic behind in your XOR is, so for dissimilar input combination it would give you the logical one. For similar input combination it will give you the logical 0. So hence it is A bar B or of A B bar. So it has taken as a product term where here A value is 0 represented with complement. B is 1 we have represented without complement, and we have taken this as one of the product terms since the output functional value is logical 1. So another logical 11 is obtained where A value is 1 and B value is 0. Hence we mentioned as a product term which is equal to A and B bar. Exclusive NOR is exactly complement of your XOR. So it will give you the output which is logical 1 if you have a similar input combination. So for 0 0 as well as for 1 1 it will give you the logical 1, and for the dissimilar input combinations, so here it will give different input combinations on your A B 0 1 or 1 0, it gives you the output 0. So it which is called as a equality detector. So XNOR or exclusive NOR is called equality detector. Now the operator symbol which I'm going to use for XNOR is a dot which is encircled. Now the Boolean expression is A bar B bar or of AB, or we can also write this as complement of its exclusive OR gate. Now, a binary logic circuit is a circuit which can be described by the binary variables and its logical operations. In order to analyze these all the digital circuits, so we have to connect the interconnected logical gates with the basic gates of AND, OR, and your NOT gates, and we need to transfer the possible logical 1 as well as your logical 0 inputs, and then we obtain the required output from that interconnected logical gate. So each gate could have your more than 2 inputs. So here we mentioned that 3 input, multiple input AND gate and multiple input OR gate. So where this multiple input AND can give you the output of logical 1 if all the 3 inputs are logic 1. Where your OR output with 4 inputs perform the OR operation as A or of B or of C or of D. If any input is logic 1, output of that become logical 1. If all inputs are 0, then it would give you the output of 0. So like this, by connecting your interconnected logical with multiple inputs of AND, OR, and NOT combination, we're going to design your binary logical circuits. Now, so these are some of the basic applications of logical gates where we are going to use to design your complex system, which can be implemented in different fields like in your automated industries. So now constructing your multiplexers, adders, as well as your multipliers in your digital computer. Next, to perform your several parallel logical operations. Next, we have to use these logical gates in automated machine manufacturing industries. So many applications are available using your logical gates, which can design your digital systems of combinational as well as your sequential circuits. So in the next class, we're going to discuss about the binary, using simplified equations using your binary rules and theorems. Thank you.